दीप स्पंदन तरी देवीचे 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 देवीचे
स्टार्ट व्हिडिओ ना
स्टार्ट व्हिडिओ केल्यावर तुमचा व्हिडिओ स्टार्ट झालाय. फक्त ना एकदा स्क्रीन ऍडजस्ट करून घ्या.
हॅलो माने सर. हॅलो माने सर. Hello. May I audible? Hello. May I audible?
Yes, sir. Yes.
Okay. Thank you. Uh, Sorry for late, but still I welcome all of you and good morning. Very earliest good morning. We are here for the webinar recent trends in material sciences. We are going to see that the applications of the recent materials as per the need of this age. Without losing the time, I would like to invite our principal, Honorable Dr. S.S. Bal sir, to say some words for this seminar. Over to you, Bal sir.
Okay, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay, good morning, everybody. I am Principal Dr. Bar. Welcome you all in this webinar organized by Department of Physics of my college. My sincere welcome to both the speakers, Dr. Sartare from University of Pune and Dr. Vanarkar from Gargoti, Kolhapur. The main theme of discussion is recent trends in material science. As I am a student of social science, I have not studied any material of this material science. However, my general knowledge says that material science may be a key aspect of most companies the world over. And this is a good subject for our career also, maybe in the area of applied chemistry, mining engineering, and mineral sciences. Considering the versatility and utility of the subject, our Department of Physics has kept the same for the discussion. I'm sure that we all will be enlightened by today's speaker and their expertise in this field. I once again welcome you all and wishing very best of luck for this webinar. Thank you very much. Over to Dr. R.M. More.
Thank you very much, sir. Though you are from social science, but sir, you are very rich in material science knowledge. So thank you very much. Now I'm going to introduce our today's speaker, Dr. Sharad Venalkar. Sir has completed his bachelor degree, postgraduate degree, and PhD degree from Shivaji University, Kolhapur. His work experience is about 20 years. Recently, he is working as assistant professor at Karmavir Hire Arts, Science, Commerce and Education College, Gagoti. He has a very wide research experience. He has completed his postdoctoral research at KOC University, Turkey, Iowa State University, USA, and Chonam National University, South Korea. He has received many research grants for major and minor research projects during his research work, like from Delhi, Turkey, and University of Kolhapur. He has, during his research, he has achieved many achievements and accomplishments. He has achieved the solution processed multinary chalconite thin film based on solar cell with the maximum efficiency of 6.6 percentage. He has developed the modified sealer, SILAR, sealer techniques. He has developed the method of manufacturing multinary chalcodenide semiconductor nanoparticles. He has also developed ultra-fast photocatalytic thin films He also got the superior surface morphology, which is world's second most photoelectrochemical performance, the best open circuit voltage for PLD deposited thin films, and many more achievements he has completed. He also developed the techniques and instrumentations like thin film deposition technique, spectroscopy, thin films and software, electrical techniques. This whole work he has published in various books and research papers. He has edited total of 7 books and chapters in 3 books, national, international conferences, proceedings, and all total 127 research publications he has done. He also have the Google citation at Google Index 26. He also received many awards during his research as he stood first in the University of Kolhapur. Similarly, he has received Gnan Ganga Academy Award for Best Techniques, DST Young Scientist with Research Scheme, nominated NMRE Young Scientist Award, Raman Fellowship, International Fellowship to take. He also received the award from Chemical Society, and such awards he has received during his research. He also having the membership in many research publications like IAPT, New Delhi, then New Jersey, other national, international communities, New Jersey, then Sweden, USA, Hong Kong, Canada, Romania, United Kingdom, and many more memberships he has got during his research publication, and they are at retention. He has taken many participations in even extracurricular activities also. He organized and participated in many national and international conferences. He has given the invited talks in 17 international national conferences and 5 national conferences. He has social invited talks also, about 20, international social talks 3, and many, he has also arranged the many international and national workshops and conferences. All this work is a reference, and maybe sir, I may be sorry because I have shortened your biodata. It is very long, otherwise your biodata will be a subject of webinar. So I would like to welcome you, sir. I would like to notice the participants that they should not say good morning, good afternoon, very good, etc. If they have any doubts and questions, they may ask on the chat box, which will be taken at the end of the talk, and the sir will reply for this. So may I request Venalkar sir to over to you.
Thank you, sir.
Thank
May I
you, sir.
audible? Yes, thank you very much for this nice introduction. Good morning to one and all, and thank you, Dr. Samrat Mani and all his organizing team of this seminar to invite me to deliver this talk on present advances and recent trends in material science. Before to start, may I request organizer to able me to share my screen, because I'm not able to
Yes, sir. Yes,
share
sir.
my
Yes, sir. We are
okay.
allowing you. Yes, sir. Now you can share the screen.
Yes, okay. Thank you.
Yes.
Okay. Thank you once again. Is it you can see some slides, sir?
Yes, yes, sir. Yes, sir.
Okay, okay. Thank you. So thank you once again for this nice seminar. organizing this one of very informative and nice seminar, and also inviting me to deliver talk on present and recent trends in material science. My presentations will start. Actually, I'm going to start that material science, which is interdisciplinary part of material chemistry, physics, and as well as engineering parts. My presentation will start, or I will discuss the material science. What is material science? Then what is research? What are the recent advances in material science? I'm going to touch only 10, which I can say a top 10, obviously in last 15 years. And then I will discuss one of the recent advance in material science, that is nothing but a solar cell technology. What are going in solar cell technology we will discuss, and if time permit, I will present the recent trends in solar cell technologies. Okay, so we will start from that material science. Material science is an interdisciplinary field of science and technology which deals with the study of designing and discovery of new materials, and can be applied to various areas of science and technology. It is very broad field, we can say. It involves the applications from number of scientific disciplines that contribute to creation of new materials. This field is made up of peoples with various educational backgrounds, so you can get an idea what importance of material science. So this field is made up of some persons from engineers, physicists, chemists, nanotechnologists, material scientists, and so many. So all these peoples are working together in this broad field of science and technology, which is known as a material science. In material science, we always focused on the properties of materials such as strength and hardness and flexibility. Then we are also focused on electrical to thermal conductivity of the material. Catalysis is another important aspect or property of material. Stability, low cost, easy synthesis. So all these are the properties which we have to take care as a material scientist or material researchers. And based on above properties, we can apply them, or the materials can be applied in a daily or today materials. Okay, as far as the history of material science is concerned, we will go through the what is exactly the material science and what kind of materials we can study in material science, but it is also very important to study the history. So when we look back history of material science, it starts from our origin, because our origin is defined by some materials. Human history, we can say. So human history has been defined by materials like the Stone Age, Copper Age, Bronze Age, and there are so many ages. And you notify there the age is defined by the materials like stone, copper, bronze, semiconductors, and all this. And this is nothing but the materials. So that's why I said that the history of material science starts from our origin. Even though I can say that man has studying material science since before leaving the caves. So it is a long history. It is a very old science, we can say, because the first metal tool was designed by humankind about 6,000 years ago. So it is a long history. Okay, material science. As far as the material science is concerned, we define four categories, or we classified the materials in material science into four main groups like metals, polymers, ceramics, and composites. Although there are so many other classes also, but the main classes where the material scientist is always focused is metal, because we know that metal is it is a combination of metallic elements, and metals usually are good conductors of heat as well as electricity, because there are number of free electrons in their outermost orbit, and we know that all the chemistry of metals also, they are quite strong and malleable, and as well as it shows a lustrous look when polished. So this is a property of metal, we can say. Okay, polymer or this polyester or plastic, we can say, are generally organic compound which is based upon carbon and hydrogen, and they are very large molecular structure. Usually they are very low density. They are stable also, but which are not withstand in a high temperature environment or harsh environment, we can say. On the contrary, on the other side, the ceramics, they can withstand at a high temperature or in a harsh environment. Basically, ceramic is a compound which is lies in between metals and non-metallic elements. And the main focused area for material scientist is the composite. The name itself suggests that the composite is a mixing of more than one metals or non-metals. which is a consist of more than one material type. For example, fiberglass, which is a combination of glass and polymer. And there are so many composites, we know that. As far as the material scientist is concerned, the scientist is always focused on composites. So a lot of work is carried out, or a lot of work you can find in composites in material science area. Metals and actually we can combine alloys with the metals because they shows a similar kind of properties. Alloy is a homogeneous mixture of two or more elements, and the metals and alloys have so many properties, like they have high tensile strength, they exhibit magnetic properties, electrical properties, high electrical conductivity. So these are the properties, and that's why they are used in electrical appliances and other things. Composites, on the other hand, they are made up of or combined together by producing two inherent different materials whose properties are enhanced by combining. That means suppose suppose material A. So one material has electrical conductivity X, and second materials have electrical conductivity Y. When we combine or form a composite, then the electrical conductivity we found, which is greater than X or Y along, or which is more than XY also. So this is the beauty of composite material. There are actually two main types of composite material. One is called as reinforcement type of material, like carbon or fiberglass. They have tensile properties and stiffness. That's why they are used in various kinds of devices. We will just go for them. We'll study later on. Impact resistance, this is another property of reinforcement type of composite materials. There is another one, which is we can say matrix types of composite material, which transfer the load to the first one, reinforcement type of composite materials. There are also a number of examples we can see, like PVC, polyvinyl chloride, and so many. They are also temperature resistance also, and they have a tendency of chemical resistance also. Both type of composite materials have some properties like high strength, lightweight, design flexibility. That's why they are used to manufacture the helmets as well as bulletproof jackets. Even though composite materials are used for aerospace because of their low cost, lightweight, and very high strength and high modularity. Now there is another one, as we discussed, that there are another two types of materials commonly used in material science, that is ceramic, which is inorganic or non-metallic solid, which is prepared by the action of heat and subsequent cooling, which is, we can say, type of one type of annealing and quenching and so on. There are so many examples like metal oxides. So, may I audible? May I audible, sir?
Yes, sir. Yes, sir.
Okay, thank you. Sorry for the disturbance. So the ceramics have a number of properties, like they are strong solid inert material. They withstand chemical erosion due to the acids and other part, like caustic soda and all these things. These can withstand high temperature also. That's why ceramics are used in harsh environment or harsh temperature. On the other hand, polymers are not that much applicable for high temperature applications. Polymers are, which is high molecular weight molecules made up of small repeat units, which is known as a monomers. There are two types: thermoplastics, which are processed by melting and heating, cooling, possibly by thermal stabilizing polymers, and thermostats, which cannot be melted and dissolved to be processed. There are so many vulcanized rubber tubes and bakelite and all these things, we know that. Now, in addition to the four type of materials or classes of materials, there are other types of materials are used in material science, like catalyst, semiconductors, superconductors, ionic crystals, inorganic gases, and many more. It is not a right platform to discuss all these things because it will take more than 1 or 2 hours to discuss each and every class of materials. But as far as the today's lecture is concerned, today's talk is concerned, I am interested in that semiconductor part, which is neither good conductor nor a bad insulator, we can say, because it acts as insulator below room temperature, and it acts as a conductor above room temperature. So this is a a special kind of material we can say, and which is highly useful in material science or engineering. Okay, so these are the classes in material science. Now, we will discuss some recent advances in material science, the most significant discovery of design or materials in last 50 years. We will just go through that slides within 5 or 10 minutes, and then we will discuss the main part of our talk. Okay. The list start from microscopy. We know that microscopy is a very simple technique used to see a very small object. The name itself indicates that it is a science, or it is a instrument used to see small objects. There are a number of actually microscopes are used from late night 600 ago or 700 ago. Initially, there was optical microscope. Optical microscopes are the device which use light and lenses to magnify the objects, but they have a limited magnification which cannot be used in right now, that in advanced technology. That's why people was trying to find out the more magnified microscope. So they replace this optical microscope by electron microscope, in which instead of light they use electrons, and instead of lenses they used electromagnet lenses. These type of microscopes are commonly known as electron microscopes. There are a number of electron microscope. Actually, electron microscope is a second generation of microscope, we can say. If microscopy is concerned, the optical microscope, we can say the first generation, which use only light and lenses. The second generation of microscope, which is nothing but the electron microscope, which consists beam of electron, and as well as some type of electromagnets to see a small object. They have high magnification power. There are two types of electron microscope used right now. One is a scanning electron microscope, abbreviated as SEM, and second is transmission electron microscope, which is abbreviated as TEM. Now, the third generation microscope was invented in 1986 by IBM Zurich Research Laboratory, and that was the scanning probe microscope. Actually, that is very, I think this is a good invention in material science, not only material science, for nanotechnology field also. I think it is not a bold statement if I say, if there is no this kind of metals, like this kind of instrument, electron microscope or scanning probe microscope, then I think it is not possible to progress up to this, up to this extent in material science or any science and technology or nanotechnology, we can say. So thanks to this kind of electron microscope, particularly electron probe microscope, that because of it we have progressed so many in science and technology. This this type of microscope is also known as a scanning tunneling microscope, abbreviated as STM, is not only provide the way to probe the local properties of sample directly with the nanometer resolutions, but it gives a clear idea how the structures are, how the surface are under the observations. Okay, so this is, we can say, the first recent advances in material science in last 50 years. The second, the most important discovery was giant magnetoresistance. It is a quantum magnetoresistance effect observed in thin film particularly, which is made up of alternate ferromagnetic and non-magnetic layers. Because of that giant magnetoresistive effect, there was a Nobel Prize given by so many number of scientists in 2007. And it is a giant magnetoresistance is a good way to control the electrical resistance at nanoscale using magnetic field. Actually, this is not the main task of our talk, so I'm not going into detail of that giant magnetoresistance, but it is a great invention in the material science history. Obviously, the third place, which is occupied by the very well-known technology, right now it is commercially available, and we we are using this kind of diodes, which is nothing but a light emitting diodes, or nothing but another one, semiconductor lasers. The development of the semiconductor lasers and light emitting diodes was started in 1962. In order to achieve the go green researchers across the world, we are looking for pollution-free electricity generation and a best solution of lightning to lower the electrical need and it bring quality, durability and colors. And in this scenario, LED is a strong potential for saving energy and protecting our environment. The replacement of conventional energy source with LED would reduce the electricity consumptions by many fold. That's why this kind of LEDs are used right now in telecommunication or CDs or DVDs, laser printer, barcode readers, and so many fields you see the light emitting diodes. So this is a great invention. That's why there are a number of scientists who received Nobel Prize because of light LED. Recently, the white LED was discovered in Japan also. Actually, if time permit, I will go through development of LEDs or my contribution in that field. I also tried some very little part I played in that light emitting diodes. I work with the CZTS and CTS type of material, inorganic materials, to produce light emitting diodes. But I don't know whether time will permit us to discuss this LED part or no. But this is a great invention in material science. Okay, the fourth one, this is commonly used right now. This is carbon fiber reinforced plastic, which is abbreviated as CFRP. This is a lightweight, strong material used in manufacturing of numerous products used in our daily life. Leading the charge are carbon fiber reinforced plastics, or more properly, continuous carbon fiber organic matrix composite. And this material has strong strength, extremely steep. They are made up of polymer matrix. That's why they are very tough, and at the same time they are light in weight. That's why you can see so many expensive cars, they use these kind of materials for steepness and strongness. Fifth one, this is, we know that the lithium ion batteries. This is one of the great invention we can say in the field of material science. Actually, it is hard, sorry, it is hard to remember how we cope with before laptops and cellular phones came along. This revolution would not have been possible without transition from rechargeable batteries using aqueous electrolyte where hydrogen is a weak ion to much higher energy density in batteries. Lithium-ion batteries required the development of novel electrode materials that satisfied number of consideration. Actually, I'm not going into detail of that material, but it is a great invention in material science industry. You can see the graph there, where the progress from 1992 to 2020, how the ever expanding applications of lithium-ion batteries one can see on the graph. Okay. So this is another invention or another recent advances, and a lot of peoples are working, a lot of companies are working on lithium-ion batteries. There is a lot of scope as far as the new or youngsters are concerned who are joining this webinar. They should notice this material. There are a lot of scope, and you can work in lithium-ion batteries to enhance their efficiency right now. Without carbon nanotubes, the list will not complete because this is another invention in last 50 years in material science. Although a discovery normally attributed to Izima from Japan in 1991, the observation on nanotubes of carbon had actually been made on previous occasions. However, from the excitement of the discovery of carbon-60 buckyballs in 1985, a series of carbons was discovered. Today, the remarkable and unique and phenomenological promising properties of nanomaterials place the right among the hottest of topics in material science. But we place these carbon nanotubes in sixth place. Why? Because there is still remains much sought out. There is a plenty of room, we can say, to use the carbon nanotubes in real applications. There is some issues like synthesis, purification, large-scale production, assembling into other devices. These are some issues with the carbon nanotubes. Day by day, there will be some progress, and maybe these kind of carbon nanotubes will go to a higher applications level. the following graph also shows the market scenario of carbon nanotubes. This is like electrical and as far as the electrical and electronics market is concerned, about 10.6% share of that market is covered by carbon nanotubes. And if you see the current market, around 4.56 billions of dollars is the current market share of carbon nanotubes, which is expected in next 18 years to about 13.65 billions dollars. You can imagine. So there are a lot of progress is going on. For a young researcher, this is another hot area where you can study, where you can start your research. Okay, seventh is one technique used to deposit thin films or materials, we can say soft lithography. This is the ability to fabricate functional structures and working devices in different materials in centralized to produce a microelectronic devices, particularly like data storage devices and many other products you can use or you can form by using a soft lithography. This process is almost exclusively carried out by highly specialized and complex and very expensive photolithography equipments, which is confined to the control environment of clean rooms. Okay, although it is costly, but it gives a nice results. Soft lithography makes use of simple ancient concept of stamping to produce a pattern again and again, and that is well-known technique. We know that, and it can be used on many different substrate also. It's maybe flat or curved or flexible. And everywhere you can use soft lithography to deposit your films. That's more soft lithography becomes cheap if you are using on different materials for different protocols, which offers nanoscale revolutions. And right now it is used in biotechnology as well as in medicines or so. In present COVID pandemic situations also, this will be a good option to make some protective glasses or plastics for our protection. There are also so many what we can say applications, but I'm not going into detail of that. The next material, which is nothing but a materials, a great invention in material science, which is related with the optics. We know that the beginning of this millennium brought a great excitement when it was conceivably demonstrated that the materials with negative refractive index could exist. And so many scientists are working on that, like a Mr. India. Light or at least microwaves would bend the wrong way on entering this material according to a standard understanding of Snell's law of refraction. This is like a contradictory results. This ended a long-standing arguments where materials have simultaneously negative permeability as well as negative permittivity that would leads to negative refractive index also. Very complicated. It is at the same time it's a confusing new optical words we can say, which gives a very internutritive results that can be explained by using the classical electromagnet. I'm not going into detail of that, but this is also a hot area of research, mathematical. So you can see one of the picture schematic diagram of that material. It is like made up of composite of metal wires, split rings assembled on lattice of printed circuit boards. It's good one for artificial, and there are so many applications of metamaterials. Okay. The next advances in material science, we can surely say that the solar cell technology, where you can convert sunlight into electrical energy. There is another one which is artificial sensor. In both area, I worked a little. That's why I put them in a single line, because I want to going into discussing what are the recent advances and recent trades in solar cell technology. If time permit, we will go for sensors also. So let's start for solar cell devices, which is commonly known as a photovoltaic devices. The devices which convert simply, what is solar cells? It is a simple device which converts sunlight or light into electricity. Okay, and for that we required material, which should be a semiconductor. In case of metals, we can form solar cell in long ago. but I'm not interested in that part because we are going to discuss recent trends or recent advances. So the solar cell or photovoltaic devices is a very simple device which converts light into electricity. As far as the solar or photovoltaic industry is concerned, photovoltaic system is concerned, it is made up of so many components. First of all, we have to deposit solar cell, which is a very small device, having a centimeter or micrometer in size. If we combine the solar cells in series or parallel combinations, then we get a solar module. You can see on the screen, solar modules, which is a combination of number of solar cells, which are arranged in series and parallel combinations. And these solar modules form a solar panel, which which consisting number of solar modules like 2, 3, 4, and so on. And these solar panels form the solar array, which we collectively called as a photovoltaic system. So photovoltaic system is made up of number of components starting from solar cell. And this photovoltaic system is right now used for a number of applications like electricity, generation of electricity, battery, charge controller, generation of meters, DC isolators, cables, mounting, tracking system, satellites, and number of applications where you can see photovoltaic system or solar cells are used. But as far as the recent trends are concerned, what is the another applications of solar cell irrespective of all this? So there are another area. I will just touch this area in this presentation where we can use solar cell, which is we can say a very emerging area. This is a recent trends in solar cell technology, we can say, and there is a lot of scope for new researchers. There is a lot of scope for funding. There is a lot of scope for research proposal or projects we can uh, uh, give to funding agencies. We'll discuss this area later on, but we will just go for conventional photovoltaic or solar cell technology in next few slides. As far as the solar cell background or history of solar cell is concerned, solar cell was first invented by, we can say, in 1839 by French physicist Becquerel. Uh, then after that, in 1883, the first solar cell was built using semiconductor selenium on a extremely thin layer of gold. They form a junction. But in 1954, Bell Laboratory, that was accident actually, accidentally they find out. In 1954, Bell Laboratory found that the silicon doped with, by using the same, they form the solar cell, the first solar cell, we can say. Can I audible?
Yes,
Yes,
sir.
sir.
Hello?
Yes, sir.
Okay, okay. Sorry for that. Now, after 1954, the first spacecraft to use the solar panels. Right now, we know that there are each and every spacecraft use this technology, solar cell technology, to generate the electricity. And in 1958, the solar cell was used in a spacecraft. And after 1958 till to date, there are a lot of inventions. You know that. I'm not going into that details, but we'll just go through we'll spend a very few time how the solar cell works. We'll study how this solar cell is made up of or how they work. Solar cell is a combination of p-type and n-type semiconductors. We know that how the p-type and n-type semiconductors can form. The peoples who doesn't have the physics or chemistry background, for them I will spend a few seconds. Semiconductors is a material which is neither, I already told that the semiconductor is a material which is neither good conductor or not nor insulator, we can say. They have 4 electrons in their outermost orbit. If you dope some elements like pentavalent or trivalent impurity, then they act as an conductors. But when we add a pentavalent or trivalent impurity into them, they becomes instead of pure semiconductor, they becomes n-type and p-type semiconductors. In simple language, n-type semiconductors contains electrons as a majority charge carrier, and in p-type semiconductors, holes are a majority charge carriers. And solar cell is a combination of n-type semiconductors and p-type semiconductors. So they are combined to form a solar cell. It generates electricity by using sunlight to make electrons to cross the junction between n-type and p-type semiconductors. So this is a very simple, what we can say, working. of solar cell. First, you have to take light source. For example, in our case, sun is a good example. Sorry, sun is one of the good source of light. So when sunlight shines on the solar cell, the photons, that mean light particles, they are bombarded on the upper surface which is made up of n-type semiconductors. Then these photons, which you can see in yellow balls are there. These photons carry energy down to the cell, and this energy is absorbed by the electrons, which are presented in n-type semiconductors. The photons gives their energy to electrons. That's why the electron jump the barrier between n-type and p-type semiconductors, and they escape out through the circuit by using that energy. And when they flow outside, they glow the light lamp and whatever maybe you are using outside. So this is a very simple, what we can say, working of solar cell. Just 2-3 phenomena there. Light is incidence on n-type semiconductor. The electrons present in n-type semiconductor absorb the light. Using that light, they cross the p-type semiconductor and they go out to the circuit to form a closed loop. And using by this simple structure or by this simple mechanism, electricity is generated. Obviously, this is a DC type of electric generations. Okay, I'm not going into detail. So the same thing is schematically represented here, how the electrons are activated by sunlight and how they travel from one junctions to another junctions to produce an electricity or electric current. Now, there is another one important thing I want to discuss with you. The material which is used to design a semiconductor, to design the solar cell. The criteria, there are certain criteria, like first criteria is that the semiconductor should have some specific band gap. Band gap in the sense that there is always a gap between valence band and conduction band for semiconductors and insulators. It's very difficult to spend a lot of time to discuss the band gap concept. But those who are not from, once again, from physics or chemistry background, for them, conductors are the material where the valence band and conduction bands are overlapped, while semiconductors is the material where there are certain bands, we can say, valence band and conduction band, they are separated by certain energy gap. And that energy gap is nothing but a forbidden energy gap in order of 1 electron volt to suppose 3.5 4 electron volt. If more than 4 electron volt, then this material forms an insulator. Okay. So electrons in a valence band, if you see in that figure, there is a brown dark colored band is there, and which is nothing but if you can see my cursor, this is, we can say, valence band, where plenty of electrons, free electrons are there. When these free electrons cross the band gap and goes to the conduction band, upper band, then electricity is possible. But it is a very difficult for electrons to jump from valence band to conduction band by themselves, because they don't have that energy to cross that band gap. That's why they need external energy. When they get an external energy, they absorb that energy, and with that energy, they jumps to the conduction band. And when they goes to the conduction band, electricity will be produced, electrons will be moved, and electricity will be generated. The main problem is that how to give the energy to electrons, how they jumps to cross that forbidden energy gap. There are a number of ways you can give or you can supply the energy by heating that semiconductors or heating that particular material. But in our case, in solar cell technology, we use sunlight, because sunlight have tremendous amount of energy. Light, we can say, light has tremendous amount of energy. When we incident light on that valence band, then the electrons absorb the valence band, and with the help of energy, they jumps to the conduction band and they produce electricity. What amount of energy they absorb and what amount of energy they gives, the correlation between them is given by one terminology that is known as efficiency. Efficiency is simply, this is what is the output divided by what is input. Okay, output is in the sense that in solar cell, output is given by open circuit voltage and short circuit current, which is divided by input power. The product gives you, sorry, not product, this ratio gives you the efficiency. And this efficiency is directly influenced by the energy gap between valence band and conduction band. So yes, can you hear me?
Yes, yes, sir. Yes, sir.
Yes, sorry for the interruption because there is some network error was there.
Yes, sir.
Okay, so once again I will share my slides.
Yes.
Okay, so we'll continue.
Yes, sir.
Okay, thank you. So we already seen that the energy band gap between the semiconductors or the valence band and conduction band, they are directly influenced on the efficiency. So your material should have band gap between 2 electron volt. And in that scenario, we use number of materials. Scientists use number of materials from silicon to recent perovskite type of semiconductors. Which materials are used to fabricate solar cell? Depending on that, there are 3 generations we just classified for our understanding. The first generation solar cell mainly have thick type of solar cell. They are made up of thick layer because of low absorption coefficient of silicon type of material. Initially, the solar cell was made up of silicon, N-type silicon and P-type semiconductor silicon combined together to form that solar cell. They have the thickness about 200 to 600 micrometer. These solar cells are highly efficient, but unfortunately they are costly, so they are not popularized and utilized effectively. After that, the researcher realized that irrespective of the silicon, there are a number of other materials. They can act as an semiconductors, and they can act as an the light to electricity converters. That's why they form this thin film type of solar cell, which we generally says as a second generation solar cell. The first generation solar cell was thick. The thickness of that solar cell is in between 200 to 600 micrometers. But in second generation solar cell, which is made up of amorphous silicon or CDT or CIES or CZTS, what is CIGS and CZTS, we will discuss later on. And these materials, the solar cell made up of these materials have very small thickness, around 1 to 2 micrometers. So that's why they are called as a thin film solar cell. Fortunately, they have low cost, but unfortunately, they are not that efficient as the first generation solar cells are concerned. That's why they are not commercially utilized yet. But recently, in last 10 years, this is called as a recent trends in solar cell technology. Recently, there is another type of solar cell or solar materials are right now are in applications or in research. They are commercially available also, or maybe in few years they will be commercially available. This kind of materials is known as third generation hybrid type of solar cell, which is made up of perovskite, which is organic inorganic compound. I'm going into detail. I'm not going into detail. Sorry, I'm not going to detail of that perovskite. If time permit, I will see some. We will discuss in some slides. But these third generation hybrid solar cells are highly efficient as well as they are low cost. So thanks for this new technology, which is started in 2009. Last 10 years was there, and within this last 10 years a lot of research was carried on this third generation hybrid type of solar cell. But I will show some slides of second generation thin film solar cells because I work on CZTS and CZTS and CTS type of solar cell during my postdoctoral research. So this is a first generation solar cell which is made up of N-type and P-type semiconductor. Around 90% of the market is occupied by this kind of thin film solar, thick film solar cell right. The limit efficiency is about 31%, and right now the best efficiency solar cell, which is made up of Sun Power company, reached about 22%. Right now, you can see this kind of materials everywhere around us. This is second generation solar cell. The market share of this material is just for we can say 5% only till to date. CIGS is only 0.5%. And this is a new material processing to improve the efficiency and to reduce the cost. I already told you. This is 1% expensive as compared to the silicon type of solar cell. That's why it should a lot of invention should have to a lot of research have to be done in this thin film solar cell so that we can use in remote areas also. People can afford to use a solar cell, but unfortunately this is not commercialized yet because a lot of hurdles are there. I'm not going into details of that hurdles, but till to date, sorry, CIGS type of solar cells achieved efficiency around 7 to 11%. In reality, in demo model they reach about 20%, but it is highly difficult to commercialize that CIGS type of solar. So even though CDT also CZTS also they have a low efficiency as compared to the recent used silicon technology. This is the third generation, which is made up of multi-junction cells. Third generation solar cell have different materials uh, ranging from perovskite, quantum dot sensitized solar cell, dye sensitized solar cell, tandem type of solar cell, which is combination of different materials are there. Okay, and actually this type of third generation solar cell demonstrated the efficiency around 40, which is crossing the Quasar limit of solar cell. This is a very recent trends in solar cell technology, and there are a lot of scope of research as well as. Okay, this is the future generation of solar cell. We can use printable solar cell, different colors solar cell we can make using dyes. These are efficiencies of solar cell right now. We'll just go to the next one because time will not permit us to discuss all these issues. Okay, this is top 10 PV solar producers. I'm just go through next one because there is a limited time. There are different methods used to prepare the solars, like physical methods are there, some chemical methods are there. In physical method, there is sputtering, evaporation, PLD, and so many. In chemical methods also, you can use different methods there. This is a very simple. I will just go through how to form a CZTS type of solar cell. This is just an example how to make a solar cell. For that, we used some precursors. We can make CZTS nanopowders using some copper, zinc, tin, and sulfur precursors. Then we can coat these CZTS nanoparticles over a substrate by using different techniques, annealing, and then sub backend processes there to form the solar cell. This is a schematic diagram how to form a, CZTS type of solar cell. CZTS in the sense that this solar cell consists copper, zinc, tin, and sulfur. CZTS type of nanomaterials was deposited over the substrate. Then you get the absorbent nanoparticles. There are no arrangement of grains which is required for solar cell. Then annealing, then followed by some backend processes, and at the last figure you can see very small solar cells. The fabrication process consists some steps. It is a multi-layer solar cell which made up of substrate generally made up of moly, because moly can withstand in harsh environment, on which a CZTS or CIGS or perovskite material or semiconductor can be deposited by physical or chemical method. And this is actually a p-type semiconductor. To make a solar cell we required n-type semiconductor also. Here in this case we use n-type semiconductor, CDS as an n-type semiconductor, cadmium sulfide, which is very thin, about 50 to 70 nanometer thick. Many times it is not covered CZTS. That's why there is a leakage in solar cell architecture. That's why the CDS layer is also deposited by aluminum doped zinc oxide to prevent the leakage, and then window layer. So these are the different layers deposited to form a solar cell. Right now, there are a lot of scope for new researchers to study on the N-type semiconductor, because cadmium is toxic and this layer is not fully covered over the P-type semiconductors. So there are a lot of scope to find out alternatives, to find alternate N-type semiconductors to deposit over the P-type semiconductors to form a efficient solar cell. Okay, this is actual schematic SEM diagram where you can see a different layers, moly, then CZTS, then over which a very small layer of CDS on which a zinc oxide layer was deposited. This is the high magnification images. High magnification in the sense that you can see the different layers very clearly. the moly on which a CIGS type of solar cell was, CIGS type of material was deposited, having thickness about 1 micrometer, on which just a 50 to 70 nanometers thick CDS, yellow colored layer you can see in the figure, deposited, and over which the window layer, zinc oxide layer was deposited to form a solar cell. So this is a simple architecture of solar cell. In recent, as far as the recent trends is concerned, instead of CIGS, you can use the perovskite materials. Okay, all other things maybe remains the same. There are different techniques are used to deposit these kind of materials. CZTS, I mentioned so many times CZTS, but CZTS is a simple copper, zinc, tin, and sulfur. It's combination of all these materials, which is composite, which is P-type quaternary compound semiconductor having band gap in between 1.4 to 1.5. Because of that high absorption, which is around 1 into 10 to 4 per centimeter, their thickness is in micrometer range is okay for convert the light into electricity. I'm not going into detail of that, but the theoretical PEC limit is about 32%, which is very high. CIGS stand for copper, indium, gallium, and selenium, similar structure of CZTS, but which is superior than earlier copper, zinc, tin, sulfur kind of semiconductor. And this is the perovskite. Okay, I will just spend few seconds on this because this is a recent trend in solar technology. Perovskite is the material which is a combination of some organic and inorganic chemicals or elements, precursors. Solar cell efficiency of these devices is increased from 3.8% in 2009, and today it is about 25.2%. So you can see a very large, that means we can say expansion or growth or increase in efficiency. This is just for a single junction architecture. If you combine with a silicon, then this kind of material gives you about 29% solar efficiency, which is exceeding the maximum efficiency achieved by single junction solar cell. So perovskite solar cells are therefore currently the fastest and advancing solar technology. Lot of work is going on. So you can see the number of papers, number of results, number of patents, even though there are some modules are, there are prototypes are present. Some companies are trying to launch this type of solar cell, and maybe in recent years you see everywhere the perovskite type of solar cells. And the good thing about the perovskite solar cell is that they can be composed in different colors. So you can buy solar cell of green color, red color, or whatever may be. You can, your roof of your home can be decorated by using different colors of perovskite type of solar cell. So it is a good beauty, we can say. This is what we can say, good technology. As far as the new researchers are concerned, they want to study the perovskite type of solar cell. Okay. Now the recent trend is the use of solar cell in biological field. Just few seconds or few minutes I will spend on that, because this solar cell can be used in our eyes also. The solar cell convert light into electricity. Our eyes also do the same thing. How we can see? The light comes in our eyes, and the internal parts or organs of our eyes convert the light into electricity. So they also work similar on the principle of solar cell. And as per the age or due to any cause, if our eyes gets damaged, our retina gets damaged, then what we can do? In that situation, we can use the solar cell. That means solar cell can be used in biological field, and this is the recent trends in solar cell research. That terminology is known as a neural prosthesis. That means the series of device that can be substitute the natural organisms which are damaged by artificial organisms. Okay, there are so many types like visual, auditory, then motor, then pain relief, but I'm not going because time not permit us. We will just go for the visual. As for the age, our eyes or the retina or the eyes is not that much effective. In that situation, that the peoples will suffer from partial or fully blindness because of age also. This is actually a global disease, a retinal degeneration, which is causing a severe vision loss. More than 30 million people in the world are suffering from this disease. This is increasing due to the aging of populations. And this is, we can say, one type of disease or disease caused to partial or fully blindness of the people. How the solar cell can work in that area? Before to study that, we should know some anatomy of that eyes. Eyes is consist of so many organisms. I'm not going into details that, but in short, there are retina. The main component of the solar is the photoreceptors. Actually, the internal structure of eyes consists the optical nerve fibers, which is connected to the bipolar junction. They are connected to the photoreceptor, and then they are connected to the pigments. Pigments, they are used to carry the electrical stimuli to the brain. So when we see actually any object, the process happens that the light is enter into our eyes through the exterior part of our eyes. These one, the lenses, pupil, and cornea, and all these things, and through which the light is incident on optical photoreceptors. The photoreceptor, which is made up of rods and cones. These are nothing but the rod cones and rod cells. Sorry, rod cells and cone cells. They convert the light into electricity. The biology people know that very well. For physicists and chemists, we should know that we see any object when the light falls on that cell, cone type of cell or rod type of cell. And during vision, actually, the photoreceptor plays a very important role. You can see the photoreceptor here, which is connected to bipolar neuron and pigments behind them. They play a vital role in our vision formation. It consists of rod-shaped cells and cone-shaped cells, and they are responsible for our vision. The rod cells are responsible for low intensity, and while the cone cells are responsible for colors. That's why the cone cells are made up of like different pigments, red color, blue color, green color. These are the basic colors. That's why they have different colors. Pigments are there, and the mixing of colors is happens here. You can see my cursor. So mixing of colors is happens here, and they will goes to pigment, and pigment will carry that electrical signals to the brain, and we can see the object. But the problem is that as our age, as we go older and older, during that time, our some organisms may get damaged. In lot of organism, there is a photoreceptor. This is one important organism which is also lost his photoreception power. In simple language, we can say it goes damaged, and that's why people cannot see the objects. And this is, we can say, blindness. Or there may be a partial damage of photoreceptor which cause the partial damaging of the eyes. So what we can do in this case? Okay, particularly this happens with the old peoples. The old peoples cannot see the objects clearly, or even though they cannot see the objects through their eyes, because the damage of photoreceptors. So what we can do, if the rod cells or cone cells does not work properly, or they get damaged, then how we can see the objects? The light is coming through our eyes. Our brain is active to receive that electrical signal. But the main problem is that light is coming to our eyes, but this light cannot convert it into the electrical signals, which can be read by which reads our brain, because the photoreceptor is the component which is responsible to convert light into electrical signal, and which is get damaged. So how to replace it? So in that scenario, the solar cell technologist or the researcher working on solar cell, he find out one remedy. He just replaced, or the people's researchers just replaced. This is a hypothetical model, as well as a number of researchers already carried out this kind of research. So this is a new trend in solar cell technology, we can say. So they proposed that replacement of rod and cone type of cell by a solar cell. Although we have to make the solar cell in a micrometer or say range, because photoreceptor have very small thickness. That's why we cannot use the first generation solar cell, because they are very thick. So we can use second generation or third generation solar cell. Here the red part shows the solar cell, which replace your cone cells as well as rod cells. That means we are going to replace our natural photoreceptor by artificial photoreceptors using solar cells. So this is the idea of visual prosthetics. Actually, there are a lot of study was carried out during last 10 years, we can say. Uh, there are other two methods also how to replace these photoreceptors. Many people use genetic mutations with virus. They put some virus there, genetically modified virus there at photoreceptor, and he will collect. It will collect. We can say it will collect the light and convert into electricity, and this electricity or electrical signals goes to brain, and we get the idea of what the object is in front of us. But as this is a genetical, so this has a lot of disadvantages. We know that it is very difficult to popularize this kind of method. So that's why people was or researcher was trying to replace this genetically mutations type of virus with other type of devices. And in this search, there are so many big companies was there like Alpha, IMS, and Orbis companies, and they invented second devices. Instead of genetically mutation viruses, they use some electronic devices in place of that natural photoreceptors. It is just like a pacemaker, which gives the pacemaker can be placed in near to the heart, to gives the pulses, okay, to assist the heart. Similarly, in our eyes also, some companies, some researchers designed one electronic device, and that electronic devices can be fabricated at the place of photoreceptors, and this device collect the light and it will convert into electricity, and that electrical pulses or impulses will pass through the neurons to the brains, and we will get the idea of object. But the problem with that invention, that device, is that it consists lot of complex fabrication. You can see in the figure also. Here you can see a lot of electronic components are there, and it is very difficult to place all these electronic complicated devices in the eye, because eye is very small organism. Okay, we know that. So because of that complex fabrication, it is highly impossible to put this kind of devices in our eyes. There is another one as electronic devices, so they require power. So they require a power supply, and as well as they are very expensive. That's why they are not popularized. Now, genetic mutations, they have a lot of disadvantages. These retinal devices, some electronic devices, they have like expensive complication structures are there. That's why they are not commonly used to replace the natural photoreceptors. In that case, the solar scientists or photoactive materials are used, or this is, we can say, a emerging area in visual prosthetics is concerned. Here we use photoactive surfaces, because photoactive surfaces are simple in fabrication, they are low cost, and does not require power supply, as well as there is no any disadvantages also. That's why people are trying to replace the natural photoreceptor by using simple photovoltaic or solar cell with minimum thickness. And for that purpose, we use number of materials for biointerface. There are some inorganic semiconductors can be used, or some organic semiconductors are used. As far as the inorganic semiconductors are concerned, we can use silicon-based materials or CDSE or ZNS. Their core shell structure can be used. Zinc oxide nanowires. This is the main component we required to fabricate this biointerface. CZTS perovskite or other inorganic quantum dots, we can say. I worked a little in that area. We used zinc oxide nanowires to use in a biointerface. But this is not, this results is not yet published. That's why I'm not going into details. I'm not showing in this public platform. Sorry for that. But I will show other some results of that biointerface. If my work is succeed, then in next some seminars or next in conference, I will present my result on that biointerface. But in my study, I used zinc oxide nanowires in association with Koç University, Istanbul, Turkey, in Dr. Sedat Nijamoglu's laboratory. I thank Dr. Shashi Bhushan Srivastava for this cooperation to make a biointerface. Okay, so turn back to this biointerface materials. As far as the organic semiconductors are concerned, you can use carbon nanoparticles or P3ST or PCBM or a number of materials you can use here. And the beauty of organic semiconductors are they are non-toxic. So you can easily replace the natural photoreceptors by using these kind of materials. Okay. Now the problem is that how to measure the working of your photo diode, or sorry, we can say solar cell, which act as a natural artificial photos receptor. And for that, there are two measurement techniques are available. One is electrochemical method, which simply measure the photocurrent or photo voltage or impedance spectroscopy. We place the photo cell, the solar cell in extracellular medium, liquid, and we can measure the photocurrent, photo voltage or impedance spectroscopy. And by using that analysis, you can find out that whether your material is able to convert sunlight into electricity, or which is able to replace the natural photoreceptors or not. But the real, we can say, real technique which is used to measurement this kind of solar cell is nothing, is called as a electrophysiography, is electrophysiology. This is in vivo type of technique, which use neural recording. Also, the picture shows you where your material, I put here zinc oxide material on which there are so many photoactive layer was deposited using organic and inorganic semiconductors. And this will measure that when how the photocurrent was measured is measured with the help of physiology devices. There is patch pipette and extracellular solutions is required. In simple language, we required one medium which is present in ice. Okay, that is extracellular medium, which is extracellular liquid medium, which consists sodium and potassium ions. Actually, this is an ionic process, as well as far as the biology is concerned. And many biology peoples also they can understood this phenomena because of the liquid present in our eyes mainly consists sodium and potassium ions. So similarly, in this experiment also we use the sodium ion or potassium ion containing solution known as CSF, extracellular medium, and the photo device is kept in that medium. We will fall the light on that photoactive layer. It will produce photocurrent, and this will be measured with the help of electronic circuit, electronic components. Okay, so this is a very simple way to measure. Actually, this is this makes a capacitive type of structure. I'm not going into details of that action potential, how the light, when the light is incidence on that material, how it will act and how proceed. But it is very interesting. Okay, as far as the cardiac action potential is concerned, I'm not going into detail, but I will spend a few seconds on the neuronal action potential type of part. So we know that when we get a stimuli, as far as our vision is concerned, when we get a stimuli, then there is a transaction of sodium ions from the extracellular medium. I will show in the next slides. So they will migrate from one medium to the another medium, and that's why there is a because of that depolarization, action potential is built up. This will remains at this will produce some voltage there. They will remains for a while, and just after going the stimuli out, the repolarization will happens, and the what we can say, the potential will decrease, not to the normal level, but it goes to hyperpolarization level also, and then after a certain time it will take a testing time, and it takes time. We know that it takes some time in milliseconds. That's why one object, when we see, Within that period, we cannot see the other objects. This is the biological phenomenon. We know that very well. But to produce that action potential, we required some threshold potential. In here, you can see the minus 55 millivolt. That is the threshold frequency, threshold potential. If less than that, if the stimuli is less than that threshold potential, we cannot see. That means there is no action reaction potential. If the threshold frequency, threshold potential is increased, that means the stimuli or the light coming from other source gives potential more than 55 millivolt, then we will get action potential type of graphs. Very simple capacitive graph, we can say. And by using that very simple graph, we can test our material will acts as a biointerface or no, not. Okay. This is a very good thing, but time not permit to discuss the second one, cardiac type of. Okay, so this is the membrane capacitance which I am talking with you. They contain extracellular and intracellular type of medium which contains sodium and chlorine type. Actually, this is a salt, we can say, extracellular fluid, which the ions, sodium ions and chlorine ions are separated by plasma medium. When stimuli is coming, the sodium ions will cross that membrane and they will produce this action reaction type of potentials. Okay, so these are the simple equivalent diagram of actual what happens in eyes. As far as the basic theoretical concept related to this invention is concerned, this is the electrical phenomena in biological system, we can say, which is mediated by the movement of ions instead of electrons in the solution. The extracellular and intracellular media, extracellular in the sense that the solution containing sodium ions and intracellular which containing the chlorine. All these ions are present in our that mean chemicals liquid within our eyes. Okay, so these extracellular and intracellular media are waterly salt solutions and they are very conductive to ions. At equilibrium, if there is no impulse, there is no light at all. At this equilibrium position, the force by which the electrical field is pulling sodium ions inward, which is exactly same as the diffusion forces. Sir, do we have? I can continue for next 5 to 10 minutes. Hello.
Ah, yes, sir. Yes, sir.
Okay, thank you. Okay, so we are talking about that equilibrium. At equilibrium positions, the force by which the electric field is pulling the potassium ions inward is exactly at the same as the diffusion of pushing them into outward. That means they remains at the steady state. But as long as the equilibrium state becomes non-equilibrium, that means the stimuli is coming there, the ions will move across the membranes and they will corresponding to the production of current. And this current can be measured or this current can be transferred by the interior organisms to the brain. This is the basic idea. And here in our research, we are trying to sufficient which can be read by the neural sense to read the signals by brain. Okay, so this is very simple background. This is the mechanism, what happens with this. I'm not going into detail of that, but just remember that photoactive surface should be biocompatible. It should not be toxic. There are a number of materials are present to form a solar cell, but you have to choose only those materials who are biocompatible. It does not produce any toxic effect. Biointerface should be cell powered because there we don't have that space within our eyes or within our bodies to produce extra power, give extra power to them. So they should be a cell powered without additional of any electronics media. And if you have these two essential properties, then you can make artificial photoreceptors. There is another one is capacitive photosimulation. Photosimulation in the sense that the light will stimuli to the organisms and they will produce the electrical signal and they will carry it to the brains. I think time will not permit to discuss this model, capacitive mechanism and Faradic mechanism. This is the device structure. Okay, as far as the device structure is concerned, this is the simple device which is used to produce solar cell, which can be used in biological applications, or which is biocompatible solar cell, we can say, which is made up of transparent substrate, ITO. Then you can deposit here organic or inorganic material. In my study, I deposited zinc oxide nanorods on which some organic materials was deposited, on which active layer of organic material was deposited, and then backside contacts for that is nothing but the PCBM, or sorry, not PCBM, the window layer, which is made up of zinc oxide also. Indium dope, aluminum doped zinc oxide can be used here. And this structure we can place at the place of natural photoreceptors. The simple mechanism is there. Because of light, the exciton generation is there. They will diffuse to donor to acceptor semiconductors, and then they goes to biological electrolyte media. There is a charge transport, and they will produce a photocurrent, and this photocurrent can be carried to brain by using our natural neurons. So this is a simple mechanism how they can be work in our vision, our eyes. So this can replace our natural eyes, we can say. And this is the simple capacitive results using PBS quantum dots. You see there is no capacitive properties for without PBS quantum dots in that photoactive substance. If you use the PBS quantum dots as a photoactive substance, then there is a good kind of capacitive results we can found. Thank you, Dr. Siddharth Nejamaglu and Professor Dr. Shashibhushan Srivastava for giving me an opportunity to work with them on this very interesting and very recent technology related with the solar cell. Actually, there are number of photoactive materials that can be used in this field. This is a new and recent field. Just 4 or 5 years back, this type of research is started. I think in world there is just 4 or 5 people or 5 research groups are working in this area, and hope it will replace our eyes, natural eyes, by using this solar cell. So this is a new technology where solar cell can be used. I appeal all of you, just think about other applications where you can use solar cell. Not only solar cell, you can use the traditional materials in advanced technologies also. So with this, I will stop. Thank you for giving me this time, a lot of time to discuss my results and recent advances in trades in material science. Thank you very much.
Thank you very much, sir. Thanks a lot. Very informative.
Thank you, sir. Thank you.
Sir, there are some questions.
Yes, yes, sir.
The chat box.
Okay, sir.
Dilam Shinde is asking that is SEM and SPM same?
SEM and
SPM.
no, both are not the same. SEM is scanning electron microscope, which is we can say, I already told you, this is we can say second generation type of microscope. Yeah. Which is we can use to see the surface structure, surface morphology, cross sections, images, all these things. And as far as the probe is concerned, this is used to actually see the surface structure with an advanced instrumentation. So probes are concerned. These are advanced technology as compared to the scanning or transmission electron microscope. So both are not same. In simple language, the probes are next generation of electron microscope or scanning electron microscopes.
Next question is up to you, sir. This Sadap Chitte is asking, it's a very informative session.
Thank you.
Will you please share the presentation?
Okay, so first of all, I want to take permission from other colleagues also, because this is not my own work. Yeah. This is the collaborative work. I worked with Professor Siddharth Nejamaglu in Koch University last year. I was selected there on Tubitech fellowship. and I work on that material. So I will ask them, and certainly they will permit us, and I will share
Okay, sir.
all this
Thank
data
you.
with you.
Thank you, sir. Thank you.
Thank you very much, sir. Thank you.
Vishal Kamath asked, explain more about the materials, but of course there is a time bound.
Yes,
I request you, all the participants, to arrange such webinars once again. Then Kishore Kamath,
yes,
he is again asking, sir, you mentioned that we can design roof, the roof with the different color
colors.
solar
Yes,
cell.
yes, 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 yes.
Will it affect the efficiency of solar panel as a whole?
No, 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 no. Actually, this is a new kind of solar cell, we can say, by using perovskite or quantum dot sensitized or semiconductor sensitized solar cell. But it is not commercially available. You can use this if commercially available, then you can use this kind of materials on your roof, and the color will does not affect the overall efficiency. Each and every colors have different properties. We know that, and in that case, certainly you can decorate your roof with different colored solar cell, and it will does not affect. It will not affect efficiency at all. But we have to wait for that solar cell, which is not commercially available. Hope they will get the answer. Yes.
Sir, one more question I'm taking.
Okay, sir.
CDS alternatives are being studied due to toxicity,
Yes.
where ZNSC material stands in this. Please throw some light in this area.
Yes, you can use ZNSE also, but you have to take care of two things. As far as the N-type semiconductors in thin film like CZTS or CIGS type of thin film solar cells is concerned, you have to take care of two things. One is that the band gap should be about two, like below 3 electron volt, like in between 2 to 3 electron volt. So this is the first criteria. And second criteria, it should have to fully covered over the p-type semiconductors. So if your material can fulfill all these things, then you can certainly use ZNSE. But there are so many other materials you have to try, like indium, indium sulfide or indium selenide or all other things. But there are a lot of scope. As far as the research is concerned, there are a lot of scopes to replace the CDS material. You can use ZNSE. If you have these samples, just give us that one, but it is difficult because that is have to deposit it on p-type semiconductors. But you have recipe, then you share with me. We will think about that. Thank you.
Thank you, sir. Kishore Puria is asking, what is the highest efficiency we can achieve by third generation solar cells?
Okay, as far as the third generation solar cell is concerned, the highest efficiency is about 30, because there are so many perovskite type of solar cell are available, not commercially, but at the laboratory level. They recorded efficiency about 25%. I worked in Iowa State University 3 years back, and I worked on perovskite type of solar cell, and we achieved around 20% efficiency. And right now it is about 25 or 29% if you combine perovskite with the silicon type of material in a tandem solar cell. So I can say that 30% is at now the highest one in laboratory scale, not in commercial scale.
Thank you, sir. Many of the participants have appreciated your session.
Thank you.
And I would like to thanks once again that we have thrown the light on origin of the materials right from starting, and classification of materials, importance of electron microscopes, semiconductor laser diodes, biological aspects with the solar and optical vision, etc. So it's a very informative session, sir. So I would like to say thank you very much, and over to Dr. Mane. Thank you, sir.
Thank you. Thank you.
यांच्याकडे पाठवली की आगवेकर मॅडमकडे आणि निनादकडे. ओके ओके. तो 97 नंबर आहे ना. झालं. Thank you. Thank you, Dr. More sir. Hello everyone, and thank you for joining us for the webinar on recent trends in material science organized by Physics Department of DBJ College, Chipulun. Myself, Dr. S.H. Mane. The earlier presenter, Dr. Sharad Vanalkar, giving a very good, very useful and nice information related to material science. And this,
Sir, sorry to disturb. Just speak loudly.
hello. Thank you,
Yes.
Dr. More sir. Hello everyone, and thank you for joining us for the webinar on recent trends in material science organized by Physics Department of DBJ College, Chipulun. Myself, Dr. S.H. Mane. The earlier presenter, Dr. Sharad Vanalkar, giving a very useful and more informative uh, information related to materials. Okay, now I would like to introduce today's next presenter, Dr. S.D. Sartale. His biodata was so brief, but I highlight only selected points which I have important from my side. He is working as a associate professor in the Department of Physics at Savitribai Phule Pune University, Pune. He was published 47 papers in well-reputed journals. He is working in various academic bodies and also member of so many associations. 2 MPhil students are awarded under his research guidance, and 3 PhD and 3 MPhil students are working under his guidance. Dr. Sartale sir have taken 5 research projects funded by the CSIR, Fast Track, DST, UGC and University of Pune. He is also working as a peer review for so many journals like material chemistry, physics, thin solid films and material letters. He is also honored and awards as a Japan Society for Promotion of Science Fellowship. He has selected and attended Nobel laureate meeting at Lindu in Germany and Alexander von Humboldt Fellowship. So I will invite Dr. S.D. Saratale sir. Please, Dr. S.D. Saratale sir.
Yeah, thank you very much, Dr. Mane, for very nice introduction, and also all the organizing committee members for organizing such a this webinar. We had very nice lecture by Dr. Vanalkar. He gave you the overview of all the recent advances in particularly material science. However, I'm going to talk about my work. Just 1 minute. I have to share the slide. Share screen. Can you see my slide?
Yes, sir. You just put it into the presentation mode.
Okay, just 1 minute.
can you see now?
Yes, sir. Yes, sir. It is visible. Yes.
Okay, so can you see my laser pointer also?
Yes, sir. It is visible.
Okay, fine. So my today's topic is SIRS, understanding and usefulness. So first I will discuss what is SIRS. SIRS is basically surface enhanced Raman spectroscopy. We will see very soon what does it mean. But let's begin with this. What do you mean by spectroscopy? So spectroscopy is basically what happens, the interaction of light with matter. Obviously the light will interact in different way. First thing, that the light can get reflected, it can get transmitted, it will get absorbed, or it will get scattered. And obviously the scattering can take place in two types of scattering. One is what we call elastic scattering, where the energy of the scattered wave is not changed. The another one is what we call inelastic scattering, that is what we call Raman scattering. Relay scattering is of course elastic scattering, and Raman scattering is inelastic scattering. Very briefly, I want to tell about this Raman effect, some history, because it's a very proud moment for all of us. That's the only one Nobel Prize India got for the the research carried out in India itself. Okay, so what happened, like on 16th February 1928, Raman was so confident that he sent a note to Nature Journal that we will probably observe these modified radiations from the fluctuations of molecule from the normal state. And actually they wanted to do this experiment on 27th February 1928. But however, this was not possible because the light source he was using was a sun. So by the time they arranged all this thing, the sun was set. So they did it on 28th February 1928, and which allowed them to see this, basically this means what to say, inelastically scattered radiations. And this on 29th February, the discovery was announced to the Associate Press. See, I mean, this is very important that on 8th March, Raman and Krishnan, they sent this note to Nature again, their results. But it was, like rejected by the referee, but it was published by the editor. And we know that within 2 years, 1930, C.V. Raman was awarded with the Nobel Prize. So this is, I mean, it's very proud moment for all of us. We know that. And because of this discovery, on 20th February, we also celebrate 20th February as a National Science Day. So then what happened, like we want to see that what he has, I mean, Raman used, this is a very simple instrument he used two lenses. Okay, the sunlight was a source of light, then you use two filters, and when you use another filter, you are basically essentially you are filtering out the Rayleigh scatter, means elastically scattering. So if I use the same whatever the radiations are passed, and if I use a filter which will block the radiation, and if I see still I see some extra radiations, then I would definitely say that those are new radiations coming because of the scattering from that particular molecule. So CCl4 was used at that time, and these two extra lines were observed, and therefore Raman said that they are inelastically scattered. And this is something, this experimental setup is he used the blue violet filter, and then he used this green yellow filter. And what you see that otherwise, without this filter, you see just this thing, and with this filter you can see there are some extra lines. So these extra lines are coming from the Raman scattering. So the demonstration was done by Professor C.V. Raman, and he got Nobel Prize. That's fine. But however, for research purpose, the Raman spectrometers are very expensive. The Raman spectrometer what we are having in our department is about few crore, I mean 1.25 crore. The reason is what? Because you require now, instead of sunlight, you use laser as a source. So these lasers will incident on the sample, okay, and there will be scattering. Now this scattering will have both the Rayleigh scattering and Raman scattering. Then you have this kind of filters which will filter out the Rayleigh scattered light, and you have to see the Raman scattering whatever that scattering light with respect to the energy of that particular photon, whatever this getting scattered. So these all these things are done automatically. You have to just put the sample over here and you start the laser will be inside this. The laser will come, it will fall on this, and then it will get scattered and you will get the spectrum. So it is automatically everything. The filters and everything are very expensive because you have to have very good kind of filter. However, nowadays the Raman spectrometers are getting cheaper. There are many Indian companies, they are also making Raman spectrometers which are with affordable prices of few lakh rupees. So let's try to understand what is this Raman scattering. So obviously we will always, as we know that we have two approaches. One is classical approach, the another one is quantum mechanic approach. So we know that light essentially it's an electromagnetic wave where the electric field and the magnetic field, which will be perpendicular to this electric field, it is oscillating with respect to time with a certain frequency, and that frequency decides the color of that particular light. Okay, so this particular electric field, so obviously electric field effects are more prominent, so we only consider electric field, of course, but there is magnetic field as well. So this electric field, what will happen whenever it will incident on a molecule, the molecule will also, it will produce a dipole because of the electric field. And this dipole will start to oscillate with the same frequency. If they start to oscillate with the same frequency, then what will happen? You will get the elastic scattering and this will again emit the electromagnetic radiations, which will have the same electric, the frequency, whatever the incident radiation had. So therefore, there will be no change in the frequency or wavelength of that particular incident radiation. However, when we do this, very proper calculations we do, what happens? This is what we call the dipole moment. Okay, so this dipole moment, this is polarizability. Okay, and this is the electric field associated with the incident light. So if you are having more intense light source, you will get more intense scattering. Obviously, that's very obvious. But that particular scattering is not only depends upon the electric field, it also depends upon the polarizability. So if your molecule is not able to polarize, if it is not going, there is the dipole moment is not going to create and it is not going to oscillate. If there is no oscillation, what will happen? You will not get, for example, the dipole need to be oscillated, and if these oscillations are they are is matching with the incident wave frequency, then you will get this first term. So alpha is also important. Okay, the polarizability, that is the ability of the molecule to polarize, means it will form the dipole moment. And of course, if your electric field is more, then obviously the intensity will be more. So this is mu, is basically tells you the intensity of the scattered waves. Now what you can see that the first term gives you the frequency, which is incident frequency. However, when we go for this, that the second and third terms, what you are going to see that this is second term has the initial, incident frequency plus the frequency coming because of the vibration of molecule, and the third term coming because of the incident frequency minus the frequency of the vibration of molecule. So what does it tells you? That there is a change in energy, either the energy is increased, or because E is equal to h nu. So the frequency is the frequency is increasing means energy is increasing. Frequency is decreasing means energy is increasing. Decreasing. Or in other words, if the frequency is increasing means the wavelength is decreasing, and so on and so forth. This is vice versa. But this is, of course, we can see that there is a change in frequency. So this is nothing but Raman scattering, one elastic scattering. The intensity depends upon what? But now the intensity depends upon, naturally, it depends upon the electric field associated with the incident photon, or we can say that the intensity of the source, whatever you are using. However, there's another term which is coming like this, not alpha, but it is d alpha dq, means it is the change of polarizability with respect to the coordinates. What coordinates q is, we will see that. So this is a generic coordinates we call. So generic coordinates will have, like if you are talking about the scattering, this vibration, what kind of vibrations you are considering, those will decide the q. We will come to that point very soon. So obviously I can see that this relay scattering, no change in wavelength or frequency. It depends upon E naught and it depends upon alpha naught. Okay, alpha naught is the polarizability of that molecule. However, the Raman scattering, where there is a frequency is getting shifted, either positive or negative, so there is a change in energy. It depends upon E naught, but it depends upon change in polarizability, not just alpha, but d alpha by dq. So why, what do these molecular vibrations, for example, we know that the molecule will start to vibrate at different types of vibrations, the symmetric vibration, stretching, asymmetric stretching, scissoring, rocking, and so on and so forth. Okay, so what happens, like this kind of different vibrations gives you some frequency change in that. So I'm coming to that point. Now, change in polarizability d alpha by dq, where alpha, I told you, the polarizability is the ability of the molecule to polarize, means to form the dipole moment. Q is the generic vibrational quantity. Suppose if it is stretching, then it will be R. If it is bending, then it will be theta, and so on and so forth. So depending upon what kind of vibrations you are considering, there will be this Q will be considered as R or theta or like that. So let's see, I mean, why some of the vibrational modes are Raman active, some of the vibrational modes are not Raman active. It's mainly because you have to see the whether your polarizability changes with that particular vibration, I mean that particular generic coordinate. For instance, if the vibrations are symmetric, so there is a symmetric stretching. Okay, so the molecule need to be symmetric. In that case, what will happen? Suppose this is the dipole moment, this, whenever you are having this symmetric molecule. If I stretch it, okay, what will happen? There will be change in this. If I again come back to this, I mean I compress it, I will get alpha as 0. Again, if I compress it, this alpha will be negative. So what I am getting, I'm changing this d alpha by dq is basically I'm getting this as a straight line passing through the origin. Obviously, so d alpha by dq, the slope of this line is not 0, and therefore these particular vibrations where you are having symmetric stretching will be Raman active. However, if you are having asymmetric stretching, for example, asymmetric stretching means on one side you are stretching more than the other side, then obviously you will be having this the alpha. But if you stretch it in on this side, it will not be negative, but what is happening now, it will give a curve. And if it is a curve, d alpha by dq will be a tangent, and this will be, which is parallel to this q line, and therefore our x-axis, therefore this will be 0. So asymmetric stretchings will not be Raman active. So some modes, the vibrational modes are Raman active, some modes are Raman inactive. So depending upon that, okay, you, for a molecule, you know that, okay, some modes are Raman active. So you will definitely get the Raman peaks because of this particular frequency. There is another approach to understand this Raman scattering is the quantum mechanical approach. So quantum mechanically, we know that for atoms or molecules, you are having molecular orbitals. Okay, so these are all molecular orbitals. So there is, like you can consider the electron is initially present in one of these, electronic states, which we can call them ground state. And you consider any state which is, virtual state, which is, at higher energy. What will happen? These electrons, okay, whenever the photon will come and incident on this, depending upon the energy of the photon, what will happen? These particular electron will go to the higher energy state and it will come back. Okay, it will, if it is coming back to the same energy state, it will be released again because there is no change in energy. The electron was is excited from this state to this state and it came back to this, or from this to this and it came back to this. However, what can happen, like if the electron was going from this state and it went to this virtual state, any state which is at higher energy state, it will, instead of coming back to this state, it came back to this state. What does it mean? There is this much energy is decreased. Okay, so this is the energy is decreased in this case. However, in this case, what happens? The photon was excited from this state to this state, and while coming back from this state to this state, instead of going to this state, this came back to this state. So if it is coming back to this state, what does this mean? There is an increase in the energy of the scattered photon. This particular scatterings, which we call Raman scattering. So this is something we from quantum mechanically also we can see that. And the Stokes lines are the scatterings where the energies decrease. So when the photon, the electron excited from the ground state to this state, instead of coming to this state, it is coming to the higher energy state. So the energy is decreased. Those Raman lines are called Stokes line. And those Raman lines basically, because this is a unique frequency, you see that, because the difference between these two energy states will give you the Raman scattering at only particular frequency or wavelength. Therefore, I'm calling Raman line, okay, so or peak. And for anti-Stokes lines, what will happen? The electron will excite from this to this state, and it will come back to this. So there is an increase in the energy. Therefore, those are called anti-Stokes line. So if I plot it on energy axis or frequency axis, what will happen? You will get this relay scattering where you are not getting any change in energy. So this is new excited, and there will be like whenever the energy is increased, so new excited is the frequency of used for the excitation of this molecule plus the vibrational frequency. So this will be anti-Stokes lines, and this is the frequency is decreased by the vibrational frequency. This will be called the Stokes line. So higher energy, lower energy. The probability, you can see that the Rayleigh scattering is most intense. Okay, as compared to Stokes and anti-Stokes, it is much higher. However, if I compare with the anti-Stokes, the Stokes lines are more intense than the anti-Stokes. Therefore, usually we use Stokes lines for our Raman spectroscopy. So you see that this is a typical Raman spectrum of CCl4. What you can see that this is the Rayleigh scatter. So this is what usually we plot the Raman scattering, okay, with the Raman shift, with where the x-axis is wave number. You can always find out, like wave number is 1 upon lambda, energy is h nu, and you can always convert wave number to energy to wavelength or frequency and all these things. There are different ways people use this. Usually we use this Raman spectrum with the wave number 1 upon lambda. So therefore the unit is centimeter inverse. So this centimeter inverse, you can see that. So the Stokes lines will be positive wave numbers if it was, and the anti-Stokes lines will be on the negative wave number. You can see that those lines, these Raman peaks are appearing at exactly same frequency. For example, it is 500, it is also minus 500. So the spectrum what we usually see, it is a Raman spectrum on the positive Raman shift. Actually, you can see the anti-Stokes lines also, but their intensities are very weak. Therefore, we usually go for the Stokes lines. And also we always start with the 100. Why? Because your Raman's, this Rayleigh scattering will be huge as compared to this intensity, because now I have cut it here you can see that. Why? Because otherwise this will be like like zero. It will be like a noise. You can just see that it is a straight line, because as compared to this axis, because this unit will be too high, this will be almost zero. So we always start with 100 or 200 or whatever it is, wave number to whatever the range you are having, 200, 1000, 2000, like that. So obviously you can just see that this Raman spectrum, or Raman spectroscopy has a lot of application. The most important application is because we call it is, this Raman frequencies are fingerprint. So fingerprint means what? Like we say that, this Aadhaar card, everybody has, very unique identification number, or you are having unique fingerprint. So therefore you can always find out, this person is changed or not. Similarly, what happens like in the Raman frequencies are also their fingerprint. Means every molecule has very unique characteristic Raman frequency. Therefore, I can always, it's easy to identify the material by just observing the peak positions. Not only that, if there is any change in Raman peak frequency or wave number, we can always say that, because why it is getting changing, we can always understand that there must be some chemical interaction with the molecule, and therefore what is happening, the frequency or Raman wave number is getting changed. We can also see the crystal symmetry or orientation of that particular single crystal material. For nanomaterials, if the width of this Raman peak is increasing or decreasing, this is mainly because of the size and shape of the nanostructure. That's also we can see. Intensity wise, if you are having this hybrid materials, composite materials, and so on and so forth, or a thin film, but I can see that if the intensity is increasing or decreasing, it will be depend upon the amount of the material. So I can always qualitatively or even quantitatively find out the amount of material from Raman spectrum. Most important point is that this Raman spectrum can be useful for any sample, solid, liquid, and gas. So it is very important that I don't need to worry about the state of my material. Another important factor is that it is non-destructive method. Non-destructive method is because then I can use this the same material after performing Raman spectroscopy. I can use it for other application. Therefore, for the forensic department, it is very important because forensic department has some, like the evidence. For example, there was an accident or something, some crime has happened. So that evidence they can take the Raman spectrum, but that the Raman spectroscopy will not damage the evidence. So later on, suppose somebody challenged to that evidence, they can produce that evidence without, there will be nothing will happen if I take the Raman spectroscopy. So far so good. Okay, Raman spectroscopy was what we say that it's very nice. It can be used for all sort of samples, for identification of the material, understanding the chemical state of the material, some stress, strain, some effects, temperature effect, these and so on and so forth. However, this major limitation of Raman spectroscopy is what? Is that the most of this, these scattering is occurring with the elastic scattering. Is almost 10 raised to 7 counts. Okay, out of the, suppose you are having 10 raised to 7 photons are incident on the sample. 10 raised to 7 photons will be elastically scattered. Only 1 photon will be inelastically scattered. That is Raman scattering. Again, in this Raman scattering, you have to understand there will be Stokes lines and anti-Stokes lines. So Raman scattering is very, very weak, and therefore, if I want to detect the material which is very, very small, for example, like I want to, we will see later on that some of the things like the impurities or some toxic elements and this and that, if I want to find out, or some viruses, bacteria, and so on and so forth, then this Raman spectroscopy will have some limitation. So these limitations, so therefore Raman spectroscopy was mainly used for the bulk materials, or single crystals or this and that. But however, what happened, like in 1974, it was kind of this Professor Fisherman, what he did, he put, this is just pyridine molecule, Raman spectrum. You can see that there are 2 peaks which are about this position. I can see that this is 1030 and 991 centimeter inward. When he put this pyridine molecule on the silver electrode, this is silver surface what he took. What he saw that these 2 peaks are very weak, and there is a huge peak coming from the silver oxide, actually 1025. And then what he did, he just did that, he gave some electrochemical treatment to the silver surface, and because of the electrochemical treatment, there was some electrochemical etching. That etching actually caused the rough silver surface. And when he optimized, when he did this treatment to different voltages, what he observed that when he gave 1 volt treatment, you can see that this silver oxide peak, which was coming at the center, it gets decreased, and at 1 volt, so if I give you -1 volt treatment, okay, so that treatment I'm not interested. What we are interested in, that if you make the surface properly rough, what you can see that you just see the pyridine molecule Raman spectrum, but not the silver oxide. So this intensity is too much high as compared to the silver oxide peak, and therefore I can able to detect. This is very small amount of this. It was 0.05 molar of aqueous pyridine solution. He could observe the pyridine Raman spectrum, and then this was a very extraordinary result. Very small amount of pyridine I can measure on silver electrode, and then people started to discuss, or the debate start. Why it is mainly because of the roughness of the sample, of the surface of the silver, or it is because of the silver itself. Was it because of the roughness of the silver, or something like that? So people started to use different surfaces, different roughnesses, and so on and so forth. And now we know that, and this is something, why? Because this Raman spectrum, which has the very small intensity, because of the rough surface of this silver, the intensity got increased too much. You can just see that this intensity got increased too much, and therefore this is what we call surface enhanced Raman spectroscopy. The name was given by as SERS, surface enhanced Raman scattering or Raman spectroscopy. And now we are aware now, because I told you that there are a lot of people started to work on this, understanding this source, why there is enhancement in the Raman signal, and so on and so forth. And now we know there are two different enhancement mechanisms. The one is called electromagnetic enhancement. The other one is called chemical enhancement. So this electromagnetic enhancement is coming because of the surface plasmon resonance, LSPR, of the plasmonic metal nanoparticles or plasmonic metal surfaces, which we know that silver, gold, copper, aluminum is also there, but that's not coming into the visible region, but in UV region. So there are certain metals, they show the plasmonic resonance peak in the visible region. Those metals or those metal surfaces with the rough surfaces, because when you make this rough, actually you are creating the nano structures on the surface. That time it was not, people were not aware why it is happening, but now we know that if you can make a nanostructure surface of these metals, then you will have this surface plasmon resonance, and in that case what will happen, these plasmon will oscillate with the certain frequency, and if that frequency is matching or which is close to the incident radiations, then what will happen, there will be the enhancement in the electric field. Now the electric field will be enhanced by two ways. The first electric field is associated with the electromagnetic wave. That electric field will be enhanced because of this plasmon resonance, and then you will have this enhancement in the electric field, and this electric field enhancement will cause the change in dipole moment, and that will give you the enhanced intensity. Another enhancement is also there, that is what we call the chemical enhancement. So chemical enhancement will occur whenever the molecule will be chemiswap with the metal surface. Now there's a chemist option. When we call it is a chemist option, of course we know there is a physics option and chemist option. Chemist option means there is a charge transfer between the surface and the molecule. Whenever there will be charge transfer, you will have this, the chemical enhancement, which will be like the contribution for the chemical enhancement is very big. It is 10 raised to 2 to 10 raised to 3. However, the electromagnetic enhancement, which is because of this surface plasmon resonance, it is of the order of 10 raised to 11 to 10 raised to 12. So this is very significant contribution from this electromagnetic enhancement. Very briefly, I will just talk about this surface plasmon resonance. You know that it will be oscillate. If you take this absorption spectrum, you will get a peak at certain frequency, what we call the surface plasmon resonance. And you know that this surface plasmon resonance is basically decide, or it is responsible for the color of the metal nanoparticles, and therefore we can get different colors of this metal nanoparticles. I'm not going into the details of that. So what I told you, that the intensity depends upon this dipole moment. This dipole moment depends upon alpha and basically E, but Raman scattering, it is d alpha by dE. Okay, or d alpha by dr, or d theta, or d phi, and so on and so forth. Anyway, this change in polarizability will not in your hand, because it depends upon the nature of the molecule, whether that molecule has symmetric vibrations or it has asymmetric vibration. If there are symmetric vibration, those will be Raman active and you will get it. If there are asymmetric vibrations, you will not able to see any Raman spectrum. However, the intensity depends upon the electric field. Now the electric field, if you want to have more electric field, of course you can change the intensity of laser, but you have limitation, because if you are having higher intense laser, what will happen, this will destroy the molecule, because most of the time this laser will, if you have very high intensity laser, this can destroy, especially for the biological molecules, for polymeric molecules, and so on and so forth. So those molecules are not stable if you expose to very high intensity laser. Therefore you have limitations on the intensity, but this electric field, due to this plasma frequency, this will increase, and you will get the increase in the intensity. So how do you do this? So and then why, because this, I told you that it gets very huge enhancement in the Raman intensity. This was many people started to do this kind of research. So you just see that this is the Ramchandran Dasari from Germany. What they have done, they actually found out that that a single molecule can be detected with this surface enhanced Raman scattering. Not only that, this was like used for melamine detection, because these are the the adulterants used in this. It can be used for this the toxic elements in the water. It can be like used for this vibro this is some biological molecule. This can be used for this cocaine, for these drugs and all these things. It can be used for HIV DNA. It can be like sugar, glucose. It can be used for this the pollutant methylene blue. It can be used for molecular and cellular. So basically, for many different varieties of applications, this search has been used by many groups, like biological groups, chemical groups, physical groups, and so on and so forth. So there are many people work on different types of aspects of search. The first aspect is to understand how this search is the enhancement is occurring. The another aspect is to develop this kind of rough surfaces or the nanostructure surfaces, which will give me the search enhancement. And of course, I can use this search for different applications. So theoretical investigation, experimental investigation are going on in all over the world. And now we know that how this search can be used for many applications. So that's a very simple way how the search measurements are taking place. What you do, you take a nanostructure surface, then you absorb these molecules which you want to probe. So we call them the probe molecule. Okay, this can be adulterant, it can be viruses, it can be some pesticides, or it can be you are interested in some molecules, whatever this molecule. These are probe molecules. You absorb on this nanostructure surface, and then you excite this nanostructure surface with the laser for measuring the Raman spectroscopy. So when you are measuring the Raman spectrum, okay, so Raman spectrum, you require a laser. Now this laser will do two things. This laser will actually oscillate. This plasmon will start to oscillate. This will give me the electric field. This electric field, and because there are some Raman active modes, those Raman active modes will have more intensity and this will be detected by this detect. So how we do that, this cartoon will tell you that how effective this method is. For example, if I take this is the probe molecule, I'm having this rhodamine 6G molecule, which I put it on the glass substrate, okay, a glass surface, and I have the laser which is 532 nanometer. I excite this, okay, so this is the incident wave falling on this R6G molecule. What will happen? There will be scattering. Now this scattering will be Raman scatter, of course Rayleigh scattering and Raman scattering. I'm interested in Raman scattering, so I have shown only Raman scattering. Of course, the spectrometer will filter out the Rayleigh scatter and I will get the scattering wave. So there are some Raman active modes. Those Raman active modes will give me this Raman scattering and I will get this Raman scattering, which I will detect. Okay, so this is what the wave number I'm having on x-axis. This is the intensity. You can see that this intensity is about 0. This is only simply noisy spectrum. However, when I put this this silver nanoparticles, okay, and on that I will absorb this rhodamine 6G molecule, and if I take again the Raman spectrum, you can see that initially the intensity was 0, now it becomes 80,000. So from nothing to everything, that's what we can get. So the same molecule, the concentration of the molecule was same, it was absorbed. Now if you absorb on the silver nanoparticles, you can get 80,000, otherwise you will get only 0. So it's very important, so very small amount of this rhodamine 6G molecule, which is toxic, by the way. If I that is this is a dye, we are having from the cloth industry. So therefore we have to be worried about this concentration of this dyes. If it comes to in the drinking water, it will be a problem. Okay. Another thing, what we know that this is a huge enhancement. I already told you that 10 raised to 14 to 10 raised to 15 times. But one important aspect is that you just see that this is the theoretical calculations made. When we are having this is a silver nanoparticle. Let's say this is another silver nanoparticle. Okay, and what you can see that the electric field we have theoretically or by simulation we have found, and the red color tells me that it is the most intense, and the blue color tells me that it is not means it is weak. So what you can see that it is higher in between these two two nanoparticles. It is of the order of 10 raised to 8. But if you go away from this metal surfaces or metal nanoparticle surfaces, it is decaying very fast. It is from 10 raised to 8 to it is going to 10 raised to 5. What does this mean? That it means that if you are going away from this, nanoparticles, the intensity of this Raman peak will decrease, and therefore we call this particular region is called the hot spot. Now, what do you mean by this hot spot? Now, the hot spots are very close to the metal nanoparticle surface. So what you can just see that you have to have this metal nanoparticles without capping agent. If you are having capping agents, this capping agent will actually block, which will have some thickness around the metal nanoparticle. And this thickness will actually increase the distance of the, because now you suppose this is the capping agent I'm having around this nanoparticle. And if I put, this is, let's say this is what I'm having, the probe molecule. Now, if this distance is higher, so what will happen? Actually, the enhancement will be lower. So this is of course one aspect we have to see. Another aspect is that if you are having the spherical nanoparticles, again this is the simulation, but you can see that this red color is everywhere around this metal nanoparticle surface. But if I am having, for example, these two nanoparticles are merged, let's say that these 4 or 5 nanoparticles are attached, and they form this nano rod. What will happen now? There, this particular enhancement will occur only at this edges. If it is a like cubic or triangular and these things, what you can see that these red regions are not everywhere on the surface. So there's the hot spot will be only here and here and here. For the star shape, this will be only here, and so on and so forth. So we have to understand this thing, that if I want to do this surge measurement, I have to have these nanoparticles of spherical shape with a certain shape, size, and they should be separated with each other. Not, they should not merge with each other. Also, their separation should not be too much. So these are all these things, like uniform size and coverage without surfactant plasmonic nanoparticle is the requirement to get most intense surge substrate. What we are doing, and of course, like I told you that I mean, this is like many people from the colleges, they are listening this particular webinar. So I'm sure you don't have much facilities. You can of course I can go for sputtering, evaporation, and there are many methods which are most expensive, but they give good results. But we have developed in our laboratory a very simple methods. One is called successive ionic layer adsorption and reduction. That is what we call SILAR, where what we do, we put this substrate in this solution of metal ions, then we dip it again in the reducing ion solution, and that's how we can get these silver nanoparticles grown on this. You can have silver, you can have gold, you can have silver gold, and so on and so forth. Most important aspect of the SILAR is that you don't need to have this glass substrate, the flat or rigid. You can have flexible, you can have porous. For example, we could grow these nanoparticles on paper, on clothes, on plastic, and so on and so forth. Another method which we have developed is the spin coating. In spin coating, what we usually, that spin coating is used for oxide thin films and all other substrate. I mean, different types of material, but it was not used for metal nanoparticles. What we did, we have spin coated this metal salt solution, and then we reduce it either chemically or in thermal reduction. The major advantage of this spin coating is that I can get these nanoparticles, very uniformly sized nanoparticles. You can see that this is what this same image of that. Very large area, about 1 centimeter square. This will be uniform everywhere. Of course, this is same for SILAR also. So both are having some advantages and disadvantages. I will not go into the detail, but something like that, you can see that these two techniques can be used. I'm going to show you now the same images of this silver nanoparticles grown by SILAR. What you can see that this particular the surface plasmon resonance that absorption with respect to this optical absorption spectrum. Okay, what you can see that this for the smaller nanoparticles, when you grow with 10 cycles, you are getting this dipole, and there is also quadrupole, because this quadrupole tells me that some of the nanoparticles are attached with each other. And if you increase the cycles, what is happening, that this quadrupole is getting enhanced, and you are getting this dipole is getting diminished. Now with this absorption spectrum, I can understand the surge. What you can see that now, I'm having this 532 nanometer laser, which I'm using for actually the record this Raman spectrum. What you can see that for 5 cycles, Okay, the intensity is 60,000. For 10 cycle, it is almost, more than 80,000, like 90,000 or whatever it is. Then again, it is getting decreasing. What does it mean? That I have to have the absorption, this the localized surface plasmon resonance peak should be close to the incident wavelength. Otherwise, I will not get the most intense, surface the Raman enhancement in the Raman peak. So I can get the most intense SIR spectrum for 10 cycles, and I have already shown you that it is 0, which is becoming now about 80,000. So this how we have, we understand, we optimize the silver nanoparticles, which will give me the more, intense Raman signal. The same thing what we can do, like this is one way, like you can measure this surface plasmon resonance optical absorption, and you can tell that, okay, which one will be more intense. Other way is that you can measure the size of these nanoparticles, and you can do the simulation study. These simulations will tell you that, this is the Raman signal, this electric field, and this electric field can tell you that how much enhancement you will see. That also one way, other way to do that. What we can do this, I can measure now this. Once you have optimized this, you can just see that this methylene blue is a very toxic dye, which if it is present in the water, it is not good for our health. So I have to have some technique which will able to detect this very low concentration of methylene blue. So you can just see that if I'm having 10 to minus 10 molar of methylene blue, and this is 10 to minus 1 molar of methylene blue. If I put that on glass, I will get the intensity as around 600 to 700. If on the other hand, even though the concentration of methylene blue is 10 to minus 10 molar, I can get the intensity of 2000, more than 2000. So it is, like 3 times higher, even though the concentration is 10 to 9 times lower. It is 10 to minus 1, 10 to minus. So I can measure ppb, parts per billion, 10 to minus 6 millions, billions, and minus 9, or even 10 to minus 12 molar of methylene blue with this kind of search. So it is very important, like another aspect we should have, this is the reproducibility. I should have get the reproducibility of this. So therefore, this large area substrate is very important. You can, like this grow this nanoparticles on a paper. You can take small pieces and you put this, methylene blue or whatever you want to measure, and you can get the SIR spectrum. So this should be reproducible, means at different positions I should get the same result. This is another aspect we should have. Repeatability means what? I should get the repeatable results, means I can, different batches, I can grow these silver nanoparticles on, suppose, one paper, another paper, third paper, fourth paper, sixth paper, seventh paper, and all these papers should give me the same result. That's also very important. Reusability is another aspect which people are worried. Can I reuse the substrate? Means if I detect this dye, can I reuse it again? For example, for this chromic red is the dye which will actually, which does the only physics option, and therefore you can say that if I do this detection, this search, I can wash it. If I wash it, simple wash with water, I can get zero intensity. Again, I put this dye, and I can get again intensity. Again, I wash it, again I detect it and wash it. It means what? There is no chemical enhancement, only electromagnetic enhancement, which means this dye is actually physics off with the surface. On the other hand, if it is methylene blue, you can see that if I just wash it, I still get some intensity. Again, I do the detection, again I wash it, the same washing, what we are doing here with the water washing. I'm not getting zero intensity. It means that for the methylene blue, where you are having this electromagnetic enhancement as well as chemical enhancement, I will not able to just reuse it by just washing with the water, but I have to do something else. What I can do, like I can grow these silver nanoparticles on this zinc oxide. Okay, and what will happen? This, of course, this zinc oxide, this silver nanoparticles will have this, this most hotspot. Basically, this electric field will be more. But however, only zinc oxide will not have any electric field enhancement, because it is not plasmonic material. But what we can do now, we can put, I mean, incident with the UV light. You know, there's this ZNO is well known as a photocatalyst. I can use zinc oxide, TiO2, or some other metal oxide nanotube, nanorods, and so on and so forth, which are photocatalytically active. What will happen when you know, exposed to this UV? What will happen? This will basically, sorry, what is happening? I don't know. This will be basically give me the degradation of this. Somebody is writing, please stop that. Okay, so this will basically give me the cleaning of the, what will happen, this adsorption, then I will expose this surge, and then I will have UV. Because of the UV cleaning, what will happen, this will be this will basically clean it. So you can just see that after UV clean, I will get only this zinc oxide peaks, and then again I can record it. So reusable surge can be made. Milk is very important. I will have only 5 minutes. So this milk is very important for all of us. And but what happens, like people adult, they put some adulterants in the milk, and this another, you know, very bad adulterants people use is melamine. So melamine is very bad, which is otherwise, you know, that this is used for this furniture, melamine dinner set, you know, and on this melamine floor and so on and so forth. It's of course very cheap. You can just think of, because this melamine dinner set, you can buy it, you know, very cheaply. I mean, very, very cheap. But this is what happens. This melamine is actually increases the, and actually falsely, you know, if you have all these techniques, you know that, you know, most of the in dairy, what you do, you go there, they will tell you that what is the fat level, what is the protein content of the milk. If that protein content is higher, you will say that this milk is good, you know, like if it is, you know, 3.2, 4.5, and so on and so forth. Accordingly, we know that, you know, the buffalo milk is better than the cow milk, because the buffalo milk has more protein content. So the whatever the, you know, method we use for measuring the whether to, you know, classify this milk is good or bad, is to measure the protein content. So what happens, melamine actually increases the protein content, and we will say that, okay, this milk is very good for me. However, if that protein content, you know, is increased due to the presence of melamine, it will be a biggest problem. So people are not aware, but there was a big scandal happen in China in 2008. What happened, like in 2007, this melamine, because we all know that, you know, now we are boycotting Chinese products, but Chinese products are cheaper, and therefore many US people were, you know, using this pet food which was imported from China, because it was cheaper, and they caused that, you know, lots of dogs and cats, they were having kidney failure. In 2008, the China itself was victim of this particular melamine. Almost 3 lakh babies, you know, like were, you know, victims of this melamine adulterant milk. 54,000 babies were hospitalized, and 6 babies died because of the kidney stone. So melamine was causing, although it showed the higher protein content in the milk or milk formula that gives to the baby, basically it was causing the problem to the kidney. And many people countries stop Chinese dairy product, and obviously like what we are doing now, the Chinese have. So it was like, you can just see that these Chinese officials were discarding melamine tinted milk. All milks were, you know, actually they discarded. There was the situation that no, you know, in China there was no milk in the shelf, because all the milks what they were selling, it was contaminated or adulterated with the melamine, so that the you know, the protein content was high. Obviously, then our government also, you know, like now have issued the guidelines, that they say that, okay, if the melamine is, you know, above this 0.15 milligram in 1 kilogram of for the infant formula, or 2.5 milligram in 1 kilogram of other milk powder, and so on and so forth, this will be a crime. It is not allowed. Then of course we know that this is there is a bill now which will give you the huge punishment, or, you know, like life imprisonment, or huge financial fine. So now we know that, you know, like, okay, if somebody does that, melamine is added in the milk, he will get the punishment. The major question is, how will you detect it? Because whatever the techniques we are having, that will tell you that this milk is good, because it gives you the higher protein content. So we have to have another technique. The source is very good in that. What we have, I mean, these are our results. We are working on that. What you do that we intentionally add melamine, this milk adulterated with melamine. We centrifuge it. We take this suspension, and if you put this suspension on our substrate, these are the silver nanoparticles. What you can see that if I put on a glass or some other surfaces, this melamine, like this Raman will give me zero intensity. But if this melamine, adulterated milk, this, suspension, what we have, if we put it on this substrate, what you can see, I will get like 30,000 intensity from 0 to this point. And I would like to tell you that here the melamine what we have added, it is up to the limit of set by FSAI. So even the lower limit melamine can be detected here. So what I have to have, I have to just get this milk, I have to put it on this, and I have to record this Raman spectrum, which is very easy. Not only that, this can be used for finding out the pesticides, because most of the times, that farmers spray pesticides, so that there will be no these insects. So these pesticides, of course, like some of the fruits, I cannot, give some heat treatment. So for example, apple, I have to eat as it is, if I can boil it, I can boil it, or I can just simply wash it. But by just washing, can I get rid of this pesticide? That's a question. So if I want to find out whether those pesticides are there or not, what I can do, that I can grow this, this metal nanoparticles on an adhesive tape, and I can just, put this adhesive tape on this, and very small amount of pesticide is enough for me, because the search can detect even 10 raised to minus 10 molar or 10 raised to minus 12 molar. So that small amount of pesticide, I can take the search and I can find out. So this search has like people have used for apples, oranges, and some even vegetables also. Now I'm coming to the COVID-19, because why we are having this virtually, we are connected with each other. It is webinar we call. Otherwise we will be having seminar. It's because of this this COVID-19. So like this Arizona University research team, they already started to use this surface enhanced Raman spectroscopy or scattering to test this kind of COVID-19 test. There is already one review article published where they say that this surface enhanced Raman spectroscopy or scattering, it helps to understand the interaction between pharmaceutically active compounds with pathogenic germs and biological organisms, and thereby it may contribute to the development of target specific treatment for the currently spreading coronavirus disease. So SIRS is very useful in that case also. Okay, there is one article from the Chinese group. So I will conclude here. These novel nanoparticles can be used as a substrate for trace detection of environmentally toxic dyes, as well as the food adulterants and harmful pathogens. But there are 4 R's are very important. You have to have this substrate, means the substrate on which you will put the probe molecule, and then you will take the Raman scattering. So these 4 R's are this, it should be robust, so that I can grow these metal nanoparticles on any surface, like the cotton, or for example, this COVID-19, you are having this swab. So the same swab can be coated with this silver nanoparticles, and you can take this swab, you take this, COVID-19 sample, and you take the search, if you can detect immediately. So you have to have robust, it should be repeatable, then reproducible and reusable. So all these 4 R's are very important for us. So I thank you for your kind attention. And this same thing was published in Sakar. My PhD student Imran Sheikh is basically working on this Raman scattering search. So I thank. If there are any questions, please ask.
Hello, sir. Hello.
Yeah.
There are 3 questions is asked. One question is, does the wavelength of laser affects the Raman spectra?
Actually, see, the laser what you are using, it actually doesn't affect the Raman spectrum, but certainly it affects the material. For example, what will happen, the fluorescence background will be more if you use because the fluorescence comes for certain molecules, fluorescence is the biggest problem. The fluorescence will also cause decrease in the intensity of Raman scattering. So you have to choose the wavelength of laser such that it will not give you the fluorescent background. It will not damage the sample. For example, if your material, suppose your material has band gap of close to 535 nanometer, naturally what will happen, instead of getting Raman scattering, that will get absorbed by the material. As such, we have seen that from classically and quantum mechanically, the energy of the photon does not cause anything, because all radiations will get Raman scattering. However, there are certain other phenomena which phenomena will block or which will depress or which will diminish the Raman scattering. So you have to choose that accordingly.
Okay, thank you, sir. One more question. Does the LSPR spectra depends on the AGNPS?
LSPR spectrum for what?
Depends on the AGNPS.
What is that? AC?
AGNPS.
Silver nanoparticles. Oh, sorry.
Silver.
Of course, because LSPR depends upon silver, because see, the localized surface plasmon resonance is the phenomena you can observe for the metal nanoparticle. Now, this LSPR depends upon three things basically: the size of the metal nanoparticles, shape of the metal nanoparticles, and in which medium it is, means the dielectric medium. So you have to see the Me theory of that. So if you put these metal nanoparticles in different matrices, for example, if I put it in SiO2 or in water, in air, and so on and so forth, so the dielectric medium, all these three factors decide this LSPR peak. So LSPR peak, of course, depends upon these metal nanoparticles, and the LSPR peak position, whatever that energy what you are having or the wavelength you are having, if your Raman scattering laser in wavelength is close to that particular LSPR, you will get this surface enhancement, this surface enhanced Raman scattering.
Okay, okay. Thank you, sir. Thank you, sir. So, yeah, have you any questions from audience? Okay, sir. No questions, sir. Thank you, sir, for your nice and information and explanations on Raman spectra. So here I will conclude today's webinar. I express heartfelt thanks to Dr. Sharad Vanalkar and Dr. S.D. Sartale for your expertise and sharing your ideas with beautiful manner. Thanks for guidance and support given by our Honorable Chairman Sri Mangetji Tambe and Principal Dr. Sri Krishna Bal, IQAC Coordinator Dr. Shilpa Sapre Bharmal Madam, and two Vice Principals Dr. Sanjay Gawale Sir and Dr. M.S. Chanda for giving me an opportunity to organize this auspicious webinar. So once again, I will thank you on behalf of DBJ and Department of Physics. Once again, I would like to thank my technical supporting staff. Without you, this webinar would not have been possible. Thank you very much for participants. Thank you once again for making this webinar a success. Thank you very much. Feedback link is in the chat box. Please fill up that feedback form as early as possible.
Okay, so finally session is over, Now participants can leave the meeting by themselves.